Headlines scream about record-breaking concentrations of gold and battery metals hidden beneath the ocean floor, promising a new era of resource abundance for our electric future. It sounds like we have found the treasure, yet if you look at the industry today, no commercial mine exists. The bottleneck isn't geology or regulation, it is mechanics. We possess the maps to find these nodules, but we lack the robotic hands precise enough to pick them up without destroying the very ecosystem that generates oxygen in the dark. To understand why deep-sea mining remains a story of promises rather than reality, we must first confront what lies on the seabed. These are not loose piles of gravel waiting to be swept into bags. We are talking about polymetallic nodules containing record levels of manganese, nickel, cobalt, and copper, critical inputs for every lithium-ion battery in existence. However, these rocks sit embedded within fragile ecosystems that function as what scientists call dark oxygen generators. They produce oxygen without sunlight or photosynthesis, acting as the respiratory system for the deep ocean floor. The tension here is physical. To extract this invisible gold, you cannot simply drag a machine across the bottom. You must separate individual nodules from their neighbors with millimeter precision to preserve the biological engine that sustains them. This elevates the engineering requirement from simple excavation to delicate ecosystem-preserving surgery. And right now, no deployed autonomous system can perform this task at scale. Current industry attempts rely on remotely operated vehicles, or ROVs, designed for brute force rather than finesse. These machines are built to drag heavy collectors across the seabed, a method that causes catastrophic disturbance to the seafloor structure. An analysis in IEEE Spectrum highlights a critical hardware failure. Existing systems lack the specific class of autonomous manipulators required for high-grade extraction. When you try to mine these nodules with blunt instruments, you disrupt unknown ecological cycles and destroy the dark oxygen generators we just mentioned. The result is that even though billions are invested, the technology remains stuck in development hell because we cannot touch the seabed without breaking it. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This mechanical failure is compounded by a deep disconnect between how engineers test their robots and what actually happens on the ocean floor. For years, the industry has relied on simulation benchmarks known as deep-sea treasure to optimize robot performance. A recent study from the University of Antwerp reveals that these models are dangerously oversimplified. The research team found that current simulations fail to account for real-world constraints like energy trade-offs and uneven terrain navigation. The flaw is in how we teach robots to make decisions. In a simulation, a robot might appear to successfully harvest nodules at high speeds while conserving battery life. But these models do not capture the physical reality of manipulating objects on soft sediment under extreme pressure. The control systems rely on flawed logic that assumes perfect conditions, leaving them without the adaptive decision-making required for delicate operations in the wild. Because the simulation tells us we have solved optimization when we haven't accounted for real-world physics and energy constraints, our robots are sent to sea unprepared for the chaos of actual extraction. The problem extends even deeper into how these machines see. Unlike shallow water where natural sunlight provides a clear view, deep-sea imaging relies entirely on artificial illumination from the robot itself. This creates unique scattering effects that current computer vision models struggle to interpret accurately. A study published in 2021 demonstrated that AI trained on standard image datasets fails when faced with the murky, light-scattering environment of the abyssal plain. The robot might see a nodule as a solid rock, or it might mistake a fragile biological colony for debris. Without accurate perception, precise manipulation is impossible. If you cannot distinguish between a target and its sensitive surroundings, any attempt to grasp will result in collateral damage. This creates a feedback loop of failure that explains the delay in commercial deployment. We can find nodules easily with sonar, but we cannot extract them without destroying the environment or wasting energy on failed attempts due to poor vision. The gap between finding a nodule and extracting one is currently unsolved by any deployed system. The industry needs a new class of autonomous manipulators capable of multi-objective trade-offs that do not yet exist in hardware form, only on paper. These machines must balance speed against precision, energy consumption against extraction force, all while navigating terrain they cannot fully trust their sensors to map. Until we solve the problem of how to touch the seabed without breaking it, these record-breaking concentrations will remain just a headline story rather than a source of raw materials for our technology. The engineering reality is that we have found the treasure but lack the mechanical intelligence to harvest it responsibly. We are waiting for a breakthrough in sensing and manipulation that can match the delicacy required by the dark oxygen cycle before any mine becomes viable. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.